Assalamualaikum and salam sejahtera. I hope you're all doing fine, especially during these situations of COVID-19. Please take care of yourself, take safety measures, precautions, limit your contact, wash your hands. Hopefully we can survive these conditions of COVID-19 virus. Okay, looking at the condition now, when all classes need to be conducted using non-face-to-face platform. So I think I will be doing this like we recording video and then giving it to you and doing some online quizzes until further notice given from the faculty. Okay. So now we continue with the second subtopic in chapter 1, which is NewtonRaphson Method for solution of nonlinear equations. So as usual, your learning outcomes at the end of this topic is to analyze, identify, formulate, and solve related civil engineering problems using NewtonRaphson Method, which cover course outcome number 1 and program outcome number 2, and then you should be able to use the NewtonRaphson method to solve civil engineering method according to the required absolute relative error or true error. Further, I would like to bring you back to the introduction of this chapter, which actually the methods on how to find the roots of an equations. So basically we have two different methods. One is the bracketing methods, consists of bisection method, graphical method, false position, and incremental searches. So for the bracketing methods, we only cover bisection method in the previous subtopic. And for this topic, for the current topic, we will cover NewtonRaphson method, which is under open methods that consists of fixed point iteration, NewtonRaphson, secant, branch, multiple roots, and nonlinear systems. Okay. Now we look at the difference between bracketing methods and open methods. As we discussed before, for the bracketing methods, the estimated root is assigned in between interval of lower bound and upper bound. And as we can see, as the computation progresses, the value will be closer to the actual true value of the roots. So this method is called as converging to the actual true root value. While for the open method, it only require, or it only start with one estimated value of xi, and it can be diverged as in figure B, as you can see from xi, and then the second estimated root is xi plus 1, and for the next estimated root is around here, which is far away from the actual location of the true value. But from figure C, if the methods converging, for example here start with xi, and then the second one is the second estimated root is xi plus 1, and the next estimated root is moved closer to the actual root. So for this time, they actually more quickly compared to the bracketing methods process. A NewtonRaphson formula can be derived from the geometrical interpretation of the figure here. So if we have an initial estimated value of xi of the root, so a tangent can be extended from the point xi and fxi. And this tangent, if extrapolated to the x-axis, we can get the new estimation of the root, which is xi plus 1. So, so the slope of this tangent is actually equal to the derivation of the function fxi. So this slope, which is the first derivation of function fxi, equal to function fxi minus 0 divided by first estimated root xi minus with the second estimated root I plus 1. So this equation, when rearranged, we get the equation for determining the next estimated root xi plus 1 equal to xi minus the function of xi divided by the first derivation of the function. Then this is what we call NewtonRaphson formula. Okay, for the steps in conducting NewtonRaphson method, first of all, we need to evaluate the derivation of function x, and then by using the initial guess of root xi, estimate the new root of xi plus 1 by using NewtonRaphson formula that we derived before this. Then we need to determine the absolute relative error or true error if the true value of the root given. Then compare this error with the pre-specified relative error tolerance, which is epsilon s, and check the number of iterations. Okay, stop the calculation if the error has exceeded the pre-specified error and the number of iterations has already exceeded the maximum number of iterations allowed, or else we need to repeat step 2 again. Okay, now we look at example 5. We need to use the NewtonRaphson formula to estimate the root of function x equal to epsilon power of negative x minus x, this function, employing an initial guess of x not equal to 0. Note that the true value of the root is 0.5671439. So the true value of the root is given in the question. So for the solution, first of all, we need to derive the equation. We get here. Okay, the f prime x is equal to negative epsilon power of negative x minus 1. And so that we can calculate the next estimated root, which is xi plus 1 equal to xi minus epsilon power of negative xi minus xi divided by negative epsilon power of xi minus 1. So starting with the value of 0, we can see the iterations calculations shown in the table. So you can pause this video and then try to do this example. Okay, aside from the geometric derivation that we seen before this in the previous slide, the NewtonRaphson formula can be also derived using the Taylor series. So if we look at here, the Taylor series expansion can be represented as this equation. Okay, this is the Taylor series expansion, and then by truncating the series after the first derivative term, so that's mean we take out this part. Okay, then the equation will equal to the function of xi plus 1 equal to function of xi plus the derivative function of xi times by xi plus 1 minus xi, this one. Okay, so at the intersection with the x-axis, the xi plus 1 would be equal to 0, or you will get this formula. And after rearranging that formula, you can get this, which is actually equal to NewtonRaphson formula derived from the previous slides. Okay, next we look at example 6 for the NewtonRaphson method. This example is actually similar to the one that we already solved using bisection method in the previous subtopic. It's a float ball that has a specific gravity of 0.6 and a radius of 5.5 centimeter. The depth of x to which the float ball is submerged underwater is expressed using this equation. So by using NewtonRaphson method, we need to find the depth of x to the which ball is submerged, and then the approximate error at the end of each iteration, and the least number of significant digits, and that the answer can be considered correct. Okay, for the solution, first of all, we need to evaluate the first derivation of this function, fx, okay, to get the fx prime, f prime x. So after differentiate, we can get f prime x equal to 3x squared minus 0.33x. And then by assuming the initial guess of the function is 0.05 for the x naught, we can estimate the x1 by using this formula, the NewtonRaphson formula. So substituting all the value from the above, we can get the estimated root of x1 equal to 0.0624222 meter. Now for the absolute relative error, epsilon A is equal to the current estimated root minus previous estimated root divided by current estimated root, and we need to multiply by 100. Okay, so we get 19.190% for the absolute relative error. And for the number of significant figures that the result assured, remember that we have an equation relating the approximate error or specified error with the number of significant figures. So applying this equation and put the value of the approximate error, we can get, okay, by rearranging these two equations, we can get n equal to n much lesser than 0.4. That means the number of significant figures for the result assured to be correct is 0, because we need to get number of significant figure lesser than 0.4. So if you can try that by calculation to get a result that correct to at least one significant figure, an absolute relative approximate error epsilon A of 5% or less is needed. Okay. Now the process is repeating for the second iterations. So the estimated root x2, okay, equal to x1 minus function of x1 divided by f prime x1. So by substituting all the values obtained before, we get the estimated root of x2 equal to 0.06237776 meter. Then the absolute relative error at the end of the second iteration, by using the similar equations from before, okay, we get 0.07157%. Okay, and then applying the similar formula of estimated error and significant figures, we can get n lesser than 2.844. That means this result, the estimated root value, is actually correct to at least two significant figures. Okay, that means the answer is correct to two significant figures. And the last iterations, estimated root x3, by using the similar equation, we can get x3 equal to 0.06237758 meter. The absolute approximate error here equal to 0.00001%. And by substituting this error into this equation, we can get n value lesser than 6.798. That means the result that we obtain here is correct to at least 6 significant figures, which is 1, 1, 2, 3, 4, 5, 6. Okay, to get a more accurate results or faster process, you can conduct these iterations using Excel. Okay. A NewtonRaphson method also have drawbacks or disadvantage. So for example, in this case, a slowly converging function with NewtonRaphson method, if we have a function of x power of 10 minus 1 and we start with the initial root with 0.5, the technique is converging on the true root here to 1, but at a very slow rate. That means you need to conduct endless iterations before you get the true rate of 1.0. So this is the example of very slow rate of NewtonRaphson methods. The second drawbacks of NewtonRaphson method is divergence at inflection points. The figure shown here depicts the case where an inflection point, that is f double prime equal to 0, occurs in the vicinity of a root. Inflection point is when the curve change from concave upward to concave downward. I have shown what is inflection point in the lecture notes. You can refer to the lecture notes. So here, the point of this change actually occurs near to the vicinity or near to the actual root. So notice that the iteration that begin with x naught follow with the next estimated root of x1, and then the next one is x2, and it's actually moving away from the actual actual true roots. That's why we call it as a diverge from the actual value of the root. The third one is the tendency of the NewtonRaphson technique to oscillate around a local maximum or minimum. So such oscillation may persist, or as in the figure, a near zero slope is reached, where actually the true root is far from the area of interest. The drawbacks of number 4 is root jumping. So the figure shows that an initial guess, which is actually close to root, here or here, can jump to several locations of roots away. So instead of going to the actual root, it will jump to the other location and then moving away from the other location. Okay, this tendency to move away from the area of interest because near zero slope are encountered. So we have here about near zero slope. Okay, the last drawbacks is the zero slope. When we encounter a zero slope, obviously if we have a zero slope, which actually f prime x equal to 0, it's a truly disaster because it will cause a division by 0 in the NewtonRaphson formula. So if you get this equal to 0, you cannot you cannot solve this equation or this problem forever. So that is the drawbacks from zero slope. Okay, for the closure, please do this exercise using NewtonRaphson method. The problem is a bookshelf was made to carry books with the height range from 8.5 inch to 11 inch. The shelf length is 29 inch with a thickness of 3/8 inch and a width of 12 inch. The vertical deflection of a bookshelf in the figure given by that equation, where x is the position along the length of the bookshelf. So please refer the lecture notes which have the full version of the question. Okay, you need to find the position x where the deflection is maximum, the absolute relative approximate error, and the least number of significant digits that the answer can be considered as correct for each iteration. Please do it within the class period and then submit through the Google Classroom that I informed to you in the WhatsApp groups. Thank you.